Now in this video lecture we will go through the nature of light, right, and why all of a sudden we switched to this topic, nature of light, because we have been doing the model of atoms. We've gone through the Thomson's model of atom, right, then we studied the Rutherford model of atom. Now all of a sudden we are looking into the nature of light. Why? Right, just need to understand why we are studying this, right, so that we can develop our interest in this, because this looks like a little off topic, right, from the structure of atom, but it is not. So since we know that the Rutherford model of atom suffered serious drawbacks, right, Rutherford model of atom could not explain us the distribution of electrons around the nucleus, right, it could not tell us anything about the energy of electrons that are revolving around the nucleus, right, and it could also not explain us about the emission spectrum, or what we call as the line spectrum of elements like hydrogen and sodium, right, that emit radiations, right, when they are heated, right. So the Rutherford model of atom could not explain us the distribution of electrons around the nucleus, and the second thing is the line spectrum of elements. These are the major drawbacks of Rutherford model, right. Now scientists in the early days, right, tried to understand how these radiations, right, heat radiations, light radiations, they interact with matter, right. So interaction of matter with radiation, right. When we say matter is any substance, right, and we know that any substance is made up of atoms, right. So we will look at the interaction of radiation with matter at atomic level, right. Suppose if you heat any object, if you heat any element, say sodium, right, which is a matter, what would be the effect, right, on the at the atomic level, right. This is what we're gonna look in this topic, right. When we talk about at the atomic level, which we would be looking into how electrons are impacted when you heat an atom, when that atom receives the heat, right, or the radiation, what is the effect on the electrons, right, that are revolving around the nucleus in an atom, right. This is what we would be looking into. So matter, when we talk about matter, we would be looking at atomic level, right, and how electrons are impacted when they receive these radiations, which can be heat radiations or light, right. What is the impact of these electrons revolving around the atom when they receive this heat, right. And based on these results, right, based on the result of interaction of matter with radiation, right, what Niels Bohr did, because Niels Bohr declared the final structure of atom, Niels Bohr used these results, right, of interaction of matter with radiation in order to describe his model of atom, right, in order to put forward his model of atom. And the Niels Bohr model of atom is improvement on the Rutherford model of atom, right. So the Rutherford model of atom, that has undergone serious drawbacks. It could not explain the line spectrum, right, and it could not explain the distribution of electrons. So based on these results, based on the interaction of how light or heat radiation or any radiation interact with atoms, right, based on the results of this interaction, Niels Bohr improved the Rutherford model of atom, right. So we'll mention this point is important. Niels Bohr used the results of interaction of matter with radiation, right? And he used these results to describe his model of atom. Right? And mainly, and based on these results only, the line spectrum of elements like sodium, hydrogen was explained. Right. So these radiations, which can be heat radiations or light radiations, right? The interaction, when we say this is an atom, this is the nucleus and these are electrons revolving around the atom. So when you supply heat energy to this atom, right, when you say you are heating it, say you heat it, so when you supply heat energy or you are passing light, right, a light is incident on this atom, right, so this atom is receiving energy from this radiation, which may be heat or light, right? So what is the result of this energy when it falls on this atom, right? How these electrons behave when these waves or when these radiations interact with the atom. This is what we're gonna study in this lecture. Now, in order to understand this interaction, right, because based on this interaction only, the line spectrum of elements was explained, and Niels Bohr used the result of this interaction to describe his model of atom. Now, to understand this, first we need to understand these radiations, right? These are radiations, right? We need to understand these radiations, which may be heat or light radiations. In order to understand this radiation, right, we need to understand the nature of light, right? We need to understand the nature of light or heat, whatever. We need to understand the nature of, we need to understand here, we say we need to understand the nature of light, right? And nature of light was explained based on two theories. First is electromagnetic wave theory, the second is your Planck's quantum theory, right? So we need to understand two theories to understand the nature of light, which is, first is your electromagnetic wave theory, right, and second is your Planck's quantum theory. Right. Once we understand these two things, this would be clear to us, right? And once we understand this, because this theory only will explain us the line spectrum of elements. To be specific, Planck's quantum theory will explain us the line spectrum of element, and this Planck's quantum theory only will explain us the Niels Bohr model of atom, right? Because Niels Bohr used the Planck's quantum theory to explain his model of atom, right? And his model of atom is nothing but the improvement on the structure of atom that was proposed by Rutherford, right? Now, we'll understand the nature of light based on electromagnetic wave theory and Planck's quantum theory, right? Before this, let's just understand it using one example. Suppose you have one heated object, right? This is a heated object, which this heated object may be an iron rod, right? Or it may be a heated bulb, which is heated using electricity, right? It may be an iron rod or bulb, right? Heated bulb. Suppose you are standing here. This is your position, right? If this is a heated object, right, which is near to you, right, you will feel some heat radiation. You will feel some heat radiations, right? You will feel the radiations that are coming out of this heated object, right? And you can feel the heat, right? Now, what scientists and what these radiations, we generally call these as heat radiations or thermal radiations, right? Now due to these thermal radiations that are reaching to you, right, through air, you are feeling these heat radiations, because these heat radiations can travel through air, right? It does not require any material medium. Like the energy from sun can reach us, it does not require any material medium, right? Similarly, this heated radiations or thermal radiations can reach you, it does not require any material medium, and they can travel with the speed of light. These two are important things. These thermal radiations do not require any material medium. Like you see, if you throw a water in pond of water, if you throw a stone in pond of water, you will see the waves that are generated, right, in concentric circles. So actually those waves are in water, so it requires material medium water, right? But in this case, these heat radiations do not require material medium. Same as the heat radiations from sun come to us, these radiations will also reach you. So it does not require any material medium, right? And it travels with the speed of light, right? So I'll mention 2 points here. No material medium is required. Right, and it travels with speed of light, right? So these two are important points for these waves. Now scientists try to understand the nature of these thermal radiations, right? And they eventually found that these thermal radiations are nothing but they consist of electromagnetic waves, right? And these electromagnetic waves further consist of electric field and magnetic field, right? So these thermal radiations are nothing but electromagnetic waves, right? And these waves consist of various wavelengths. We'll just understand what these terms wavelength mean, right? So just try to understand till this point, right, what we are doing and how these things will help us to deduce the Neal-Bohr structure of atom, right? So we know that these thermal radiations now consist of waves which we call as electromagnetic waves, right? And these electromagnetic waves consist of various wavelengths or frequencies, right? And if you remember, we have studied in the Rutherford model of atom, there was one point where we mentioned that the electron that are revolving around the nucleus, right, the electrons are charged particles, right? So when they revolve, when they are accelerating, to be correct, they are accelerating, right? Since they are accelerating, so they will emit waves, right? And when they emit waves, the electron is losing energy because it's emitting the electromagnetic waves or the radiations. It's emitting radiations. These radiations are also nothing but similar waves, right, which are electromagnetic waves. This was proposed by James Clerk Maxwell, right? And he said that since this electron is continuously emitting these electromagnetic waves which are radiations, so the electron will keep losing energy and will finally fall into the nucleus, right, which doesn't happen. So it contradicts the stability of it, right? So the nature of these waves, so one more thing important is these waves, right? These waves consist of, I said, various wavelengths, right? These waves or these thermal radiations, now we know these are electromagnetic waves, right? So these thermal radiations are, now we know these are electromagnetic waves, and these electromagnetic waves further consist of electric field and magnetic field, right? And this electric field and magnetic field are perpendicular to one another, and these are also perpendicular to the direction of the motion of the wave. If you look at this, it somewhat it will look like this. If this is the wave, right, then the other would look like this, right? One of this is electric field, the other is your magnetic field, right? And both these are perpendicular to one another, and it's also perpendicular to the direction of motion of the wave, right? Since it consists of electric field and magnetic field, right, that is why we call it as electromagnetic waves, right? Since, I'll repeat, since these waves, these thermal radiations, scientists found that these thermal radiations consist of electric field and magnetic field, that is why we call it as electromagnetic waves. Electromagnetic is from the word electric and magnetic. These are electromagnetic waves, right? So now we know many things about these waves, right? The other important point is that these waves consist of waves of various wavelengths or frequencies. We'll just understand these terms, wavelength and frequencies. You might have studied these in physics also, right, in class 10th or class 9th, right? So you should be familiar with these terms like wavelength, frequencies, wave number, right? So these waves or these thermal radiations from this heated bulb or an heated iron object, thermal radiations consist of waves of different wavelengths or frequencies, right? So electromagnetic wave theory, what it teaches us, we have already just summarized. I'll just summarize here. We have already studied these points, those points, right, of electromagnetic wave theory. The points are that these electromagnetic waves, right, this theory was electromagnetic wave theory was put forward by James Clerk Maxwell. You should know the name of the scientist. It's James Clerk Maxwell, who proposed the electromagnetic wave theory. And what are the main points of this electromagnetic wave theory is that the energy is emitted from any source continuously in the form of radiation. Like I said here, that energy from this heated body, right, is emitted continuously, right? This is the continuous form, right? What is the discontinuous form? If the energy that is coming out of this heated object is not continuous like this, it's like this somewhat, right? There is discontinuity. This is the discontinuity. So these waves that are coming out of this heated object is not discontinuous, but this is continuous waves. So this radiation or the thermal radiations or the energy emitted from any source, right, from any source is the energy that is emitted from any source continuously in the form of radiations, right? These are radiations and is known as radiant energy. The radiations consist of, I said that these radiations, right, consist of the electric field and magnetic field. That is why we call it as electromagnetic waves, right? And the radiations possesses wave character, right? These radiations are nothing but, we said, electromagnetic waves. So these electromagnetic waves possess wave character, right? We'll just understand more about wave, some terms related to wave. So these energy or these thermal radiations consist of electromagnetic waves, right? And these electromagnetic waves consist of electric and magnetic part of it. That is why we call these as electromagnetic waves, right? It consists of electric and magnetic fields. To be correct? It consists of electric and magnetic field which are oscillating perpendicular to one another. Like I said, both these electric component and magnetic component are perpendicular to one another, right? And to the direction of propagation of wave. These waves, like I said before earlier, that it requires no material medium for propagation. Like I said here, it requires no material medium for propagation. It can travel in space, like sun rays can reach us through space. It requires no material medium, right? It requires no material medium, and it travels with the speed of light. We know that the speed of light is 3 into 10 to the power of 8 meter per second, right? So these are the main postulates or points of electromagnetic wave theory, right? And like I said, that these waves, the waves coming out of this heated object, consist of various wavelengths or frequencies, right? And if you arrange these waves, right, in an order of increasing wavelength, right, or decreasing frequency, right, what you get is your electromagnetic spectrum, right? Electromagnetic spectrum, you've been introduced in, you'll understand more about electromagnetic spectrum in physics, right? Electromagnetic spectrum is, just understand one thing here for electromagnetic spectrum, that waves that are coming out of this heated object, these waves consist of waves of different wavelengths or frequencies. And when you arrange these wavelengths in an order of increasing wavelength or decreasing frequency, what you get is a electromagnetic spectrum, right? It's somewhat like this. If you arrange these, right, in an order, like we use V, I, B, Y, O, then your R, right? This is how this electromagnetic spectrum looks like, right? V stands for violet, indigo, blue, green, yellow, orange, red, right? And the wavelength would be around 4, 450, 500, 550, 600, 650, 700, 750, right? So here in this direction, your wavelength is increasing, or we say frequency is decreasing, right? Wavelength is increasing and frequency is decreasing in this direction. And what this consists of, this is your electromagnetic spectrum that consists of waves of different wavelengths, right? So when you arrange all the waves, right, in an order of increasing wavelength, what you get is an electromagnetic spectrum, right? Now there are some little important points. These wavelengths consist of radio waves, microwaves, infrared, visible and ultraviolet, and gamma rays, right? And what you see with Georg, this is the visible portion. This is the visible portion of the electromagnetic spectrum, right? And if the wavelengths that are below this violet, right, these are known as ultraviolet waves or ultraviolet spectrum, right? These are ultraviolet waves, and above red, right, these are infrared waves, right? So here you get infrared spectrum, here you get ultraviolet spectrum. And what is Vibgyor, or what we see is very small portion of the entire electromagnetic spectrum. So visible region is a very small portion of the entire electromagnetic spectrum, right? So there are some terms now related to waves. We know that this is your wave, right? these are crests and these bottom points are troughs, right? And this is your, this point or this point is your amplitude of wave, right? And this is this point, the distance between two crests or two troughs is your wavelength, denoted by lambda, right? So the distance between two crests or troughs is your wavelength, right? These highest points are crests and these bottom points are troughs, right? And this is this point, this is your amplitude of wave, right? Now there is one important term, right, which is the wave number. You may get some numericals on that. Wave number is defined as the number of waves present in 1 centimeter length. If suppose you have this 1 centimeter length, so the number of such waves, right, number of such waves defines your wave number, right? Wave number is number of waves per centimeter, right? So if you have more waves, or suppose you have in 1 centimeter length, if you have more waves like this, so wavelength is less, right? Suppose you have less waves like this in the same 1 centimeter length, the wavelength is high, right? So wavelength, so wave number denoted by nu, right, is inversely related to wavelength, right? More is the wavelength, less is the number of waves per centimeter. Here you see you have more waves, so wavelength is less. More waves, right, more are the number of waves, that means higher is your wave number. So when you have more waves, you have less wavelength, so wave number is inversely related to wavelength. Similarly here you have less waves, right, so the wavelength is high. Less waves means less wave number, so wavelength is high, right? This is how the wavelength and wave number is related. And there is one important thing, relationship between velocity, wavelength and frequency of a wave, right? Wavelength, there is one relation which is C is equals to nu lambda, right, where C is the frequency and V is the velocity and lambda is the wavelength, right? As frequency, you know, is what is frequency? Frequency is the number of waves. If you want to describe frequency, it's the number of waves passing through one point, right, per second. In 1 second, the number of waves passing through a point is your frequency. So more is the number of waves passing, more is the frequency, right? And lambda is the length of each wave, right? Hence their product will give you the velocity, right? The number of waves, which is frequency, right, and lambda, the length of each wave, gives you the speed, right, gives you the velocity of the wave, right? So C here denotes the velocity of waves, which is the product of frequency. Frequency is, if this is the point, number of waves passing through this point, and lambda is lambda is the wavelength, right? So number of waves passing through a given point, more is the number of waves passing through a given point, higher would be the frequency. So this is the relation. You may get some numericals on this relation between frequency, wavelength and the velocity of light, right? So I hope all this is clear to you, right? Just remember the interaction of matter with radiation, right? Based on these interactions, right, we reached at some point these interactions could explain us the line spectrum, and Niels Bohr utilized these results to propose his model of atom, which we will be doing in future. The line spectrum and the Niels Bohr model of atom was explained on the Planck's quantum theory, right? And these two theories, electromagnetic wave theory and Planck's quantum theory, will tell us the nature of light.